Okay, good afternoon. Today we're going to talk about support vector machines. I'm going to split this into two sessions, but because there is quite a bit of math here in order to understand the versatility and even the beauty of support vector machines. But first we're going to start with this idea of the maximum margin classifier, trying to build a classifier in which the frontier separating the two classes is as far away as possible from all the points. Then we're going to look at what are support vectors and how we get to the shape, the equations of the support vector machine. So let's start with the maximum margin classifier. We saw when we started looking at classification problems with this gene activity and cancer example, we saw how if we wanted to place the line dividing the two classes by trying to fit, to minimize the square distance of all the points to the line, we get something that doesn't quite work because points that are far away from the frontier are pulling the frontier towards them. So actually what we want is to focus on this part here where we need to split the two classes. And so we looked at logistic regression, where we are doing a regression to try to find a function that approximates the probabilities of the points belonging to either of the classes. And so this uses that logistic function, and we can then find the frontier here on this region that matters most, because we are trying to get a high probability of this class 1 over on this side and the low on that side. However, we saw a problem here is that when we use this logistic function, if we allow the coefficient of the vector that determines that plane dividing the two categories, if we allow these coefficients to increase arbitrarily, we can make this function very steep. And so if the function is very steep, it's indifferent where the line is placed. So it can be close to one of the classes, or close to the other, or in the middle. It doesn't matter where. So the frontier is placed very loosely between the two classes. And this is a problem because if it ends up being very close to one class, this may result in overfitting, because we are depending very strongly on this point being actually the one furthest, closest to the frontier on this red class, and there being no other red point further ahead. So we solve this problem of the arbitrariness or the looseness of the frontier using regularization. So basically we force the size of these coefficients, defining our plane to be as small as possible, by adding a new term, a penalty, as a function of the size of these coefficients. So without this regularization, the frontier can fall anywhere, even very close to the point. With regularization, we force the size of the coefficients to be smaller, and we force the function to be less steep. If this logistic function is less steep, it has to be placed away from the point, and so we obtain a better, it gets stuck a bit stronger there in the middle, and we obtain a better distinction between the two classes without as much risk as overfitting. So in this case, it will always end up close to this central part here. Unfortunately, regularization with logistic regression forces us to introduce this additional penalty term over our objective function. So basically, we have this objective function which computes the probabilities that we saw previously. So we have the logistic function based on the inner product between the coefficients and all our examples, and then we compute the loss function. But then in this case, in order to do this regularization and to try to keep the frontier away from the point, we have to add this term, which is basically the sum of the square values of all the coefficients, dividing by this c, this scaling factor. So the larger the c, the lower the weight of this term, the less important it becomes. the smaller the regularization. But if the regularization is too small, then the frontier can get too loose and can be very close to the point. If we increase regularization to force it to be in the middle, then we are moving away from what our target function was, our original objective function. And now we are no longer adjusting to that function of the probabilities of the points belonging in a class, but that function plus some penalty, or in this case minus some penalty, because we are using minimization here. But in any case, we are changing our target function. So this type of regularization forces us to change the objective function in order to add this penalty here. So here we come to an important notion in how to try to solve this problem. We have a margin classifier if we have a classifier where we can compute the distance between any example and the frontier, the hyperplane separating the class. Logistic regression is an example of that. It's a margin classifier because we know where the hyperplane is and we can compute that distance. A maximum margin classifier is one that explicitly tries to maximize the distance between the hyperplane and the closest point on either side. So this is the margin. The margin is the distance between the hyperplane that separates the classes and the closest points on either side of that hyperplane. So maximum margin classifier tries to make that margin as large as possible. This forces the frontier to be exactly there. It gets stuck as far away as possible from the point, and it reduces overfitting. And it does this explicitly and not by just penalizing arbitrarily some part of what we're trying to optimize. So in this case, we have here an example. This would be the maximum margin, the result of this maximum margin classifier, the line where we maximize the distance to the closest point. And these three are the closest points to this line. So these are called the support vectors, are the ones that are determining where the hyperplane lies, because since the hyperplane is trying to be as far away as possible from the closest points, which are these three, the other points do not matter. It doesn't matter where the other points are, only these 3 points are determining where the line is. And this is intuitively what we wanted in the classifier. If we want to separate our examples in these two classes, it doesn't matter where the points are that lie far away from the frontier, as long as they are on the correct side. All that matters is that we draw the frontier between those points that are close to the separating hyperplane in a way that maximizes this distance, so that we do not risk too much by placing the frontier close to any of these points. So this would be the maximum margin classifier. It maximizes this margin here, which is the distance between the hyperplane that separates the class and the closest examples to that hyperplane. These closest examples are the support vectors. So now let's try to implement this, and we're going to do this in a way that doesn't work, but it's useful to understand why we have to do this differently. So let's consider the time distance to the hyperplane. So this is the dot product between the vector that determines the orientation of the hyperplane and its example. So if the example is on the side of the hyperplane where this vector is pointing to, this will be positive. If the example is on the other side, it will be negative. This is how the inner product works. This constant here, W0, determines where the hyperplane is placed in space. This vector determines the orientation of the hyperplane. Of course, if we increase the vector, then this term here becomes larger. If we decrease it, it becomes smaller. So, but we don't want to compute the distance as a function of how large or how small the vector is. So we normalize this value by the size of the vector. This means that the distance is always the same, regardless of how long we draw that vector. And this is a sign distance because points on one side of the vector will have a positive sign on this distance. On the other side, it will be negative. So now we can multiply this by the class. We have class -1 on one side, 1 plus 1 on the other, and this will always be positive if the points are on the correct side. And now we want to maximize the minimum distance to the plane. So points in the class +1 must be on the positive side, points of class -1 must be on the negative side, and we want the one that has the smallest distance to have that distance as high as possible. So basically we need to find the minimum distance to any hyperplane defined by these w's, and then we need to adjust the coefficients in order to give us the maximum of this minimum distance. And this is easy to implement. We just need to we create this vector with the coefficient just to do the inner product, because we need one vector in column to multiply by the matrix with all the points. So basically this is just to do that operation. And then here we do the inner product of the vector and all the points. So basically this part here. Then we add the other coefficients. We normalize this by the norm of the size of the vector. And now we return the minimum value. So we have the distances to all the points multiplied by their classes. And now we return the minimum value. And we want to maximize that. But because our function the function we are given in the library is for minimization, we just change the sign. So maximizing that distance is minimizing the inverse of that distance, but it's all the same. So basically this is trivial to compute, to implement. We just compute the distance to the closest point, and we ask our solver to maximize the distance to the closest point by minimizing minus that distance. Unfortunately, this is the result. Each time we run, we get something that is completely absurd, and it doesn't work. So in theory, this should work because we are explicitly telling the solver to try to maximize the distance to the closest point. But in practice, the solver cannot compute this result. And the reason is that when we are changing the orientation of this line, while one of the points, let's say this point is closest to the line. While this point is closest to the line, we have a distance function that is continuous and the derivative is continuous. But at some point, when we're changing the line, a different example becomes the closest one. And at that instance, there is a change in the function and the derivative becomes discontinuous. So actually, our target function looks something like this. For each point, there is a continuous surface with a continuous derivative. It's a smooth surface. But there are these edges when the line changes such that a new point becomes the closest one. And suddenly the curve changes. And since the maximum value is here, is along one of these edges, these solvers that use the derivative of the function to try to maximize or minimize the function cannot work here. We always need the derivative to know where to go along the function to find the optimum. We saw that with the least mean square approach initially. But in this case, when we use the derivative and the derivative is discontinuous, then everything goes wrong and the solver cannot converge to a solution. That's why we get this result. Each time we run, we get something different and the solver cannot find the solution. So basically this is the problem here. If we want to do a maximum margin classifier, we need to maximize the minimum distance to the points. The points change as the hyperplane changes. We get discontinuous derivatives and we cannot solve this problem numerically. So we need to change the approach a bit. And this is how we get to support vector machines. Now, the idea is simple. The problem is numerical computation. So remember that machine learning depends on the computer being able to solve the numerical part. So we need to change the problem. I'm going to show quite a few equations now, but the idea is not that you memorize the equations, or I'm not going to ask you to demonstrate this or something like that that requires just memorizing all these equations. But it's important to understand the path that we're going to follow, because then there are some important characteristics of support vector machines, the kind of results they give us and how we can use them, that we can only understand if we understand how we got there. So why we need to do these transformations, because numerically the original problem we cannot solve it, and where we end up and why we end up there. So the idea here is that you understand this reasoning that leads us to support vector machines. So one thing we can note is that when we have this normalized distance to the hyperplane, it doesn't matter how long the vector is. We can have a longer vector or a smaller vector, the vector that determines the orientation of the hyperplane. As long as we scale everything accordingly, the distance is the same. So we can arbitrarily change the value of this pseudo margin here, so this expression here, the one that is there in the numerator, we can arbitrarily change that one by scaling the size of the vector and the W0 in order to guarantee that it is at least 1. So even if it's a very small value, we just increase the size of the vector and it becomes 1. So we can impose this constraint. This part here on the top will be at least 1. And now we change our objective function. Instead of trying to find the maximum of the minimum normalized distance to the hyperplane, we simply try to find the minimum of the size of our vector. Because if we guarantee that this expression here is at least 1 for all our examples, so this is for all the x in our data set, all the x vectors in our data set, then if we can squeeze the size of the coefficients of the hyperplane as much as possible, this will force the frontier to be as far away from the point. It's exactly the same thing as we did in logistic regression. So solving this is the same as solving this one, reducing the size of the vector. We can do something even more convenient, which is reducing the square of the size of the vector. Why is this more convenient? Because minimizing a quadratic function is a lot better because it's a well-behaved function. It has that large, nice basis that we just go down the derivative and find the mean. So this is what we're going to try to do. As long as we guarantee that this constraint is fulfilled, this is important. If we manage to minimize as much as possible the size or the square of the size of our vector, then we find the optimal place of our frontier, our discriminant. So now we have a constraint optimization problem. We need to find the minimum of that function, the square of the size of the vector, subject to this constraint. This expression here with the inner product to our data multiplied by the class, this must be greater or equal to 1, for all our data points. So for each data point that we have one constraint because it must be true for all our data points, and given those constraints, we must minimize the size of the vector W. And this can be solved with Lagrange multipliers. I'm going to do a small detour just to explain this method with a simpler problem. Let's suppose we want to maximize this function here, 1 minus x squared minus y squared. We want to find the maximum of this function somewhere around here, but we impose a constraint. The constraint is that x minus y minus 1 must be 0. So the maximum we want must lie on this line. Now one thing that we can tell is that if we are moving along this line and we find the maximum of this function in red along this line, then the derivative of this function in red along the line must be 0. Otherwise we could still climb a bit more. So when we find the maximum, this line must be parallel to a contour line on the original function, the red function. The contour line are those lines that trace the points where it has the same value. In addition, when we write an equation like this, for example, gxy equals 0, this is a contour line of gxy, because this is a line where the values are 0. So basically what we're saying is that if this is one function, f, and this is another function, g, at the maximum, the contour lines must be parallel. So at this point here, the contour line of the red function is parallel to the contour line of the blue function.
Isn't there an infinite number of contour lines?
There are infinite number of contour lines, yes, but there are finite number where both of them are parallel, because outside this, you no longer find parallel between the two. So you can draw an infinite number of contour lines on the red one, but they won't be parallel to the blue line here.
We can find always one because we have an infinite number. So
yes, we find that one. So if the contour lines are parallel at that point, then the derivatives must be parallel too, must be in the same direction at least, because the derivative is perpendicular to the contour line. The contour line is the line where the points are all the same, and along that line the derivative must be zero. So all components of the derivative must be pointing perpendicularly to that line. So we know that the derivative of our objective function must be something multiplied by the derivative of the constraint, the function that gives us the constraint, in the places where we can find the maximum. This is the conventional, this minus here is purely conventional, because now we can join these two parts together and we have the Lagrangian function, which basically consists on the function that we want to optimize plus a Lagrangian multiplier multiplied by the function that gives us the constraint. So this is the Lagrangian for constraint optimization problem. You just multiply the function that gives us the constraint for each constraint by a Lagrangian multiplier and add to the objective function. And now we're going to find the critical points, those where all the derivatives are zero and our maximum, our optimum should be in one of those. So basically we're going to set the derivative to zero, and we're going to solve here these equations as a function of x, y, and alpha. When we have these three equations and three variables, when we solve them all, we find the solution for x and y. So this is how we can find the optimum of that function given a constraint using this Lagrangian multiplier method. So this is minus this is 0.5 minus 0.5 would be that point there where we meet all these conditions. So this is the idea. We're going to solve our constraint optimization problem using Lagrangian multipliers, joining everything together in a Lagrangian and then solving that problem. So what we're going to do, we have to find the minimum of the squared size of our vector, the vector that determines the hyperplane that separates the two classes. And we have this condition here, that this minus epsilon n, then the dot product of the vector by each data point plus w0 plus 1 must be smaller or equal than 0. Note that this is one constraint per data point that we have. So if we have 100 data points, we have 100 constraints that we must fulfill. So when we write the Lagrangian, we will have one Lagrangian multiplier for each data point that we have. It's important to understand where this comes from. We have one constraint for each data point, so we have one Lagrangian multiplier for each data point. And this is the Lagrangian for this problem, the function we want to optimize, and then the sum of all those Lagrangian multipliers multiplied by the function that gives us the constraint for each data point.
But that function is
no, it's just this one is greater than 1, and now
but in the Lagrangian, the Lagrangian.
I put the minus here. Okay. Just to.
I was wondering
yeah.
if it was that thing or if we want to.
No. It's correct. It's that one, but I just changed the sign here before the sum. Okay. Now we can compute the expression for the derivatives as a function of the vector of coefficients of w0. I'm not going to do this in detail, but these are the derivatives, and we can replace in our Lagrangian, and we obtain a dual representation of the problem. I'm not going to prove that this is a dual representation of the problem, because that would be too much math that is not relevant for our purpose. But a dual representation is basically a different problem that gives us the same answer. So if we maximize alpha in this one, we get the same result as the original optimization. Okay. So this is the expression that we want to, the problem that we want to solve. We want to solve, maximize the sum of all the alphas. The alphas are the Lagrangian multiplier for all the constraints that came from each of our points. So we have as many alphas as data points in our data set, minus 1/2 this sum of the inner product of all pairs of vectors, multiplied by their corresponding classes, multiplied by their corresponding Lagrange multipliers. So this is the important thing. This is what we get when we replace the expressions for the derivatives at 0 in the original Lagrangian. The constraint is that the sum of all the Lagrangian multipliers multiplied by the classes, remember that the classes can be 1 or minus 1, this sum must be 0. So the total of Lagrange multipliers for class 1 must equal the total for class minus 1. In addition, these Lagrange multipliers must be all at least 0 because they are Lagrange multipliers. So this is the expression that we get for the support vector machine. We want to find the maximum of this expression, and it's now only a function of the Lagrangian multipliers. The original values for the vector, the orientation of the vector and W0, we can get those from the constraint. But we can see intuitively what this expression means. We are trying to maximize the size of the Lagrangian multipliers, but we must do so evenly on both classes because of this constraint. Also, when we have points, examples that are surrounded by examples of the same class, this product, yn and ym, of every pair of examples, is positive, regardless of whether they are of the positive class or negative class, because if they have the same class, we multiply the two and it's positive. If the points are close together, then the inner product of the vectors determining these points will be positive, because they are pointing in the same direction. So basically, for points that belong to the same class and are close together, this term tends to be high. And since we are maximizing, and there is a minus sign there, when points are surrounded by neighbors of the same class, their alpha tends towards 0. That's the only way of preventing this penalization here. But when points have neighbors that are of the opposite class, then we have some cases where the inner product of the two vectors is large because they are close together, but the classes have a different sign. And so this becomes negative. And in this case, it pays to increase those alphas. If they have most of the neighbors are of the same class, which happens when the problem is linearly separable, when the classes are linearly separable, then this still, the penalty is smaller, but there is still some penalty when we do this operation for all the other points. So it pays to increase a bit the alpha on those points because of this term here, but not too much. Eventually it starts to not to pay off anymore. The problem, of course, happens if we have one point that is really surrounded by points of the other class. This can happen if the classes are not linearly separable, and then this has no solution, because the alpha can go to infinity. But we'll see that a bit later. So this is the intuitive...
That also is the scalar that we are going to multiply with the control line, right?
Yeah, it's the Lagrange multiplier for the constraint of each point. So we have one constraint for each point in our data set. Each point is associated to one Lagrange multiplier and are these alphas. So what we're doing here is for every pair of points, doing their inner product and multiplying by their alphas and their classes. So I'm going to show an example of how to implement this with Python. You're not going to implement this, but this is just to show the different steps on the computation. We have this, we want to maximize this function subject to these constraints. So one thing we can do is we can separate this part here, the product of the classes and the inner product of the points, and build a matrix which has, it's a square matrix with the same number of columns and rows as we have data points. So it's just the inner products of all the points multiplied by their corresponding classes. We're just building the matrix with all these products here. And now we're going to create a function to optimize. So in our case, we have a function for minimization, so we're going to change the sign. We want to maximize that. So we want to minimize this operation here, the dot product between the alphas and the product of all those, of this matrix with all the combinations and the alphas again. So basically what we're doing here is doing this computation of alpha times the other dot product for all the matrix. But we are putting this with a positive sign, and this one, the sum of the alphas, with a negative sign. The reason here is that we want to maximize, but the function we are given is a minimization function, so we just change the sign. We also need the Jacobian, which is the matrix with the derivatives, or the vector with the derivatives of all our variables, which are the alphas. But this is simply the product of the alphas by these inner products here. Minus 1 for each alpha, which is the derivative of this part. So basically, we have one line of code for our loss function, one line of code for the derivative, and now we load the data, standardize, and so on, and we run the minimization. So we set up the constraint. This is an equality constraint on the sum of all the alphas. So basically, we have this matrix with all our categories, and we are setting up this constraint. This must be 0. So we have the sum of the product of each alpha by the corresponding category, and this is merely the dot product of the two vectors. The Jacobian of this function is merely the categories, because if we do the derivative of this as a function of alpha, we just get the epsilon value. So these are the categories, and we set this as a constraint, and we also set the bound for our alphas between 0 and none. None indicates that we don't have an upper bound. The alphas must be larger than 0. So now we start with a random guess, and we minimize. We start with a random guess for all our alphas, and we do the minimization of that loss function for all our alphas. So what we are computing here is no longer directly the coefficients of our hyperplane, but we are computing the Lagrange multiplier for our data set. And the reason we're doing that is because we had to change the problem. We could not solve numerically the first one of trying to maximize the minimum distance to the hyperplane. And now in this new problem, we are solving for the alphas and not directly for the hyperplane, the coefficients of the hyperplane. This seems a bit strange, because typically we can have hundreds of points, and now it seems that we created a much more complicated problem. But it can be solved efficiently with the right methods. And in the end, we can even look at what happens for all the alphas that are not 0. Actually, I'm comparing to 0.001 because we have rounding errors. But I'm considering that all alphas below this value are 0 effectively. And we see that nearly all our points have alphas that are close to 0, except 3 points. There are 3 true values here. So these are the support vectors. These are the points that matter. All the other ones are irrelevant for this case. So here are the 3 support vectors. These are the 3 points where in the solution of that optimization we get alphas that are not 0. And now we can compute the hyperplane from those. We know that the coefficient, at the critical points where we did those expressions for the derivatives, we know that the vector of the coefficients is the sum of all these alphas multiplied by the classes multiplied by the vector of each example. But since most of the alphas are effectively 0, we can ignore most of them and just use those 3 that are not 0. Also, for those support vectors, we imposed as a constraint that the margin, for all vectors the constraint was that the margin must be at least 1. But for the support vectors the margin is exactly 1 because they lie at the margin. So this value here must be exactly 1 for the support vectors. And so we can average this for all the support vectors. We could actually solve this for any one support vector, but due to rounding errors it's better to average for all the support vectors we have. So basically, we have these to compute the coefficients. We do these computations, sum of the alphas times the epsilon, the classes, and the values of our examples. and to get W0 we do the mean of this expression over all our examples. And the examples we consider are only those that are support vectors. So we created this array first, and now actually we are calling this function with only 3 points, those 3 points that are the support vectors. So this seems a bit confusing because we are computing all the outputs, then we end up finding that only a few of them are relevant, and then we compute the coefficients of the plane from the output. But it works, and now we get the maximum margin classifier. This was explicitly computed to maximize the distance between the hyperplane and our support vectors, those points that are closer to the hyperplane. So to sum up this part, we saw that to reduce overfitting, we need to maximize the margin. Because if we don't maximize the margin can lie too close to some points, and this means that if those points are not really at the edge of the class, then we can have misclassification when we get new examples. So the farther away from the edge of the class we can put our discriminant, the less overfitting we'll have. So we saw that we wanted to build a maximum margin classifier, but we cannot do that explicitly by just computing the distance to the closest point because of numerical problems. So we converted that into that expression for the support vector machine, where we use the inner product of all the pairs on our data points, and we compute the Lagrangian multiplier for each of our data points, so all these alphas. But then, in the end, most of these alphas are 0, and only a few of them matter. And from these, we can compute the discriminant and know where the frontier lies. So we have this age matrix with all the inner products, and then we use that for the constraint optimization problem, and we get the result. Here are a few sections where you can read over this part of SVM. And now we're going to take a small break, and then go to the more interesting part of support vector machines.